Hi, in the previous video we talked about the basic idea of free falling, and here are some more questions for you to think further. Please finish this page and get back to us. Pause the video now if you haven't finished.
A few moments later.
The first part of question is asking you whether or not the time for landing or free falling will be the same or different when it is at different locations, different heights, and different planets. So you can imagine you have got an object, let's say a ball, and you want to release it at a certain height to maybe go through a certain distance, let's say 2 meter or 10 meter, it doesn't really matter. Whether or not the time between the examples would be the same. Okay, so that's the question. For the first question, it's asking you about location. So for example, Hong Kong and New York, or you can name any other cities that you like. And the answer should actually be the same time for free falling. And we are assuming that the Earth is a sphere, and so it doesn't really matter which city it is. So the answer is same, but not exactly the same. Okay, if you go to study IB physics, then you get to learn more about this. In fact, it's a bit different when you at the equator or when you are at the two pole, right? North pole or south pole. It's slightly different, but then it's not very noticeable. So in IGCSE, you can take it as the same for now first. Part B, about different heights. So for example, the ground level, or you can call it the sea level, versus the satellite orbital level. You may be thinking that, some people would tell me that, would that means outer space? And in outer space, there's no gravity. So of course it would be different because it takes infinite time if there's no gravity. I would say no. For satellite, actually, whenever they can orbit, that means there must be a certain effect of gravity going with the satellite so that the satellite can stay with the Earth. Imagine this, without gravity, while the Earth is orbiting around the Sun, then the satellite would not follow, right? It doesn't make sense. And in that case, then satellite would just be gone in that case. So there is gravity in the satellite orbital level. However, as you could imagine, it's much, much weaker. So the time, of course, will be different. I'm not saying that because of their height to land on the surface of the Earth. It's just talking about maybe passing through 2 meter or 10 meter or even 1 km, it will be different. So the answer will be different. If you are comparing not as that extreme, if you're comparing, say, the ground level or sea level versus a certain mountain, the peak of certain mountain, then there should be a difference in theory. However, once again, because the peak, it is not a lot actually. So in terms of the impact of the time difference, it's not going to be very noticeable either. But here we will try to acknowledge different heights would affect the result of the free falling time. So we'll say different here. A metaphor that you can think of is the magnet. I'm pretty sure most of you have at least played or touched a magnet before. And so if you know magnets, there are North Pole and South Pole, or you can simply put the magnet close to an iron, for example, then you find there will be attractive force. Gravity is somewhat similar here, where when you put them closer, the force will be stronger. And if you're further away, then the force will simply be weaker. Okay, very common sense and very logical. So this is also why if you are further away from the Earth, then the gravitational force will be smaller, and therefore the time for you to travel will be longer because the force is smaller. And lastly, for different planets, Moon and the Earth, obviously the answer will be different. If you ever go to the Space Museum, then you know when the astronaut are walking on the Moon is so much lighter than the one on Earth. In fact, the one that on the Moon is about 1/6 of the gravity on the Earth only. So if you try to release a certain object on the moon, then of course the time will be much longer. And I think that is also something you can observe from the video that I showed you earlier about the Apollo 15, that one. You may find that, if you use a scale to think about how tall the astronaut is and where he or she dropped the hammer and feather, then you find out the time somehow is pretty long. Imagine you simply drop a hammer at this level, then it will be much shorter on Earth. If you're asking me how come the moon will be so much less than the Earth, then my simple answer for now is because moon has much less mass than the Earth. Okay, and if you want a more detailed answer, or if you are even interested in the formula, go and study IB physics. Alright, I'll see you again 2 years later. So now, by looking at the answers of these questions, you should be able to draw a conclusion, that is, the gravitational acceleration, as known as acceleration due to gravity. That means when we talk about this, right, it's due to gravity only. So that means we are assuming no air resistance. Okay, so this is an assumption that you should put down. So when you have a significant air resistance, of course, the acceleration of the free-falling object would be different, just like earlier when we talk about the feather or when we talk about a plain A4 sheet. So they would not be the same as the other object. However, for other objects, no matter you're talking about a 10 kg lead ball or 1 kg lead ball, they will all be falling with the same acceleration, and therefore with the same height, then they should be taking the same amount of time landing on the ground. So here we will say the gravitational acceleration would be constant. However, this is only valid on the Earth's surface only, and that is to say, if you do it somewhere else, like that is really tall, or like tall as in like maybe satellite orbit, right? Not like the peak. Or if you are doing it in a different planet, then of course the free falling time will be different. For the last question, I asked you to calculate how far the ball will travel if you simply release it in the air for 5 seconds. In order to calculate this, I would suggest you to draw a graph, and also you need to know the acceleration. In case you don't know, right, you can actually find in the textbook or search it online. The acceleration that you can take for the Earth's surface is actually 9.81 meter per second square. In IGCSE, we will simplify this because this number is can simply be rounded up to 10 meter per second square. So let's just stick with this number and try to work out how far it will travel in 5 seconds. Again, I will recommend you to draw the VT graph first. So if you haven't tried that, pause the video now and try it first.
2,000 years later.
Okay, so when you draw the VT graph, then obviously this is V, this is T. Let's not forget to put down the unit, meter per second and second. And you really have to recall what you learned about the motion graphs earlier. So since V is going to be affected by acceleration for each second, so since you start with released in the air, so you will start with 0 at the beginning. After 1 second, let me draw the x-axis first. After 1 second, you end up with 10 meter per second, right? According to what you learned about acceleration. Similarly, it will be 20. I'm afraid I don't have enough space, but I hope you can allow me to do. This is not going to be in scale. Similarly, after 3 seconds, then you get to be 30 meter per second, because again, for each second you gained 10 meter per second. Okay, because acceleration is 10 meter per second square, or you can interpret this as 10 meter per second per second. So you gained 10 meter per second for each second. Alright, so that is to say for 4 seconds, then it will be 40. Alright, sorry about my scale, I didn't spell it too good. And so 50 here. And so at the end you have a relationship. Oopsie, it's really bad. It's a triangle, okay? It's supposed to be a triangle. And this is a 3D graph, okay? And well, actually I shouldn't draw this line. But then if you try to find the distance or displacement, then what you can do from the 3D graph, again, according to what you learned in the motion graph video, then that will be the line, the area under the line, and that is the area of the triangle. And for calculating this, our area, let me just put down area equal to distance travel first, and that would equal to base, which is 5, times the height, which is 50, divided by 2 because it's triangle. So the answer will be 25 times 5, so 125 meter. Okay, would be the answer. So that's actually quite a lot of time. Imagine, I mean, 5 seconds, 125 meter is like how many floors? It's just like, I mean, one floor is like 3 meter, right? About 3. Actually, 3 meter is pretty much. It's a lot already. I think it's not like let's say my flat here is not yet 3 meter. So if you try to calculate like 3 meter per floor, how many floors are there? It's gonna be 41 or 2. Let's say 42 floors. So imagine the building that we have in Hong Kong or anywhere. I guess Hong Kong is pretty tall in the top of the world. So 42 floors is actually a lot, right? It's a really tall building. If you somehow would like to drop something down there, and it only takes 5 seconds to reach there. And so yeah, 5 seconds can actually travel a long distance. However, this again, the assumption was based on there was no air resistance. However, in most of the time, even if you try to throw a coin, say a $1 coin, down, of course I'm not encouraging you to do that, but then it would be more than 5 seconds because of the air resistance. Something that we will talk about next, basically. The best way of understanding and explaining air resistance is by particle theory. So imagine this: if you get a piece of paper to be the object, and this object is moving to the left on my screen, and apparently everywhere, unless you are in space or in vacuum, there will be air particle, right? You cannot see them, but you know they exist. So normally those air would be stationary, let's say, but when you get the paper to move through them, you have to push them away, right? So during this process, we call them collision, basically colliding the paper with the air particle. Then since you are pushing them away, they must be taking the energy, or we call momentum in the future, from the paper itself. So that's why the paper will get slowed down, and this is a formation of the air resistance. Just like when you go to those kids playground, you see those plastic balls. When you try to slide down or jump into it, you get slowed down because the speed, the energy from you got transferred to the ball, and that's why you got slowed down. And so the next question that we need to think about is, what are the factors that affect the air resistance? So here I would like you to think of 2 factors that would increase the air resistance. I'll give you 10 seconds. Okay, so the first factor that you may think of is to increase the surface area. Some people may call it the frontal area, right? Which actually frontal area is more precise wording, because when you talk about a paper, then probably it's okay. But then when you talk about say a plane or anything, for example my cup here, so let's say my cup is 3D, right? So if you talk about surface area, it's basically the whole cup, right? And so if you move through the air, in fact only this surface will be colliding with the air. the area at the back and also this handle has nothing to do with the collision with the air, so they should not be accounted. So using the word frontal area probably will be, well, it is more precise than surface area. However, surface area would already be accepted in IGCSE. So this is the first factor that you can think of, and I would like you to actually do an experiment, very simple experiment. Just grab a piece of paper, any kind of piece of paper. You can then test this. You can try to use your hand with a piece of paper to kind of move this around and try to feel the air resistance, right? You should feel a little bit of friction, but that is like against your movement. And then you can kind of open the paper. I mean, earlier you fold it, and then later on you open it, and you try to feel it again. You find it, this time it's a bit harder to push through. I mean, if you try to use an even bigger one, then it will be much more significant. So make sure you try that out yourself and try to feel the air resistance yourself, not just a theory, but also feel it. Next, the second main factor for increasing the air resistance will be greater relative airspeed. Okay, then you may be wondering, what does that actually mean by relative airspeed? Think about this. When the paper, again, I'll use this as an example, you can again experience it as well. When you try to move the paper through the air, like I said, if the air were stationary, then the relative airspeed is simply the speed that you are moving. However, there are chances where you may have headwind or tailwind, and that may affect the rate that you collide with the air. And so in that case, for more precise wording, then we should be talking about the relative airspeed. In a more lower level way of saying it, like a simple way of saying it, then you maybe just talk about the object's movement. However, this is relative actually, so I will actually prefer to say the relative airspeed, or in the case where you find the air is actually stationary, then I guess you can just talk about the object's speed or velocity. So let's just try to experiment it yourself. Try to get a piece of paper once again with maybe a certain area significant enough. Then what you can do is you can try to move slowly, and you don't feel much because yeah, that wouldn't be a lot of air resistance. But if you try to go for it quickly, or not only you hear a loud sound, but also when you try to push through it, it's harder as well, and that means there's a greater air resistance also. So make sure you try it out yourself and feel the air resistance. So I hope just now you have experienced the two mini experiment where you try to increase the surface area and also increase the relative airspeed to see whether or not you can really feel the air resistance got increased. However, those are just empirical evidence, right, from the experiment only. They don't actually explain through very fundamental law. So we actually still need to think of a way to explain why this happens, right? And so that's why, like I said, you have to think from the particle theory point of view. And so now I would like to give you some time to think about, for these two factors, how you can explain these two factors will affect the air resistance like the way we said. So please pause the video now, think about it. I would like you to write it down, and I'll explain the answers to you.
A few moments later.
The first reason is actually very simple to explain. Imagine you got a bigger piece of paper, so like increasing the frontal area or surface area. And then again, air is everywhere, right? So when you move through this bigger piece of paper, then obviously you are colliding with more numbers of air particles. So that's why air resistance will increase. So this is the explanation. You can write it down. I'm not going to write it. You can write it down somewhere on your note. Next, for the relative airspeed, then you can think about this. When you had a slower speed, so let's say it is 1 cm per second, let's say when I just now move it, versus 2 cm per second, so that is faster. Think about the volume of the air that I cover. So let's say in 1 cm I can cover, let's say I also double the area, that is how much of volume of air that I move through in 1 second. If I move quicker, then obviously this layer will get thicker, right? And obviously that's gonna be more air that I have to go through, and of course that must be harder. And so in this case, there will be more air resistance experienced by the piece of paper in such a higher speed. Again, please put down the explanation in particle theory in the space there on your note. It will be helpful for you in the future when you explain this. Alright, lastly, let's try to do this exercise and we will end this booklet. So yeah, try it out yourself and I'll explain the answers with you. Pause the video now.
A few moments later.
Alright, so the first quick question is not about the graph, so let's just do this first. It said the stone dropped from rest and what is the speed after 1 second. So obviously, I'm pretty sure you know how to do it, 10 meters per second. I think these are just so easy, then you can just write down 50 meters per second. So each second you gain 10 meters per second. And that will be the answer, or I blocked the question, so I guess you mark it already. Question 2 is that now it got thrown downward with 20 meters per second. So imagine the ball or whatsoever, the stone actually, 20 meters per second. And then the downward acceleration is g, which is 10 meters per second squared. So they are on the same direction. That means you already got 20 and you now add on 10 every time. So in that case, that will be 30 meters per second after first second, 40, and then this one will be 50 plus the original 20, that is 70 meters per second. Very simple. And lastly, now is that the stone is actually flown upward with 20. So in order to present it better for yourself, you may want to take it as negative 20, and then when you go down, it's actually plus 10 every time. So you had negative 20 original because it's going up, but then the acceleration is going down, and so one of them has to be negative. And so in this case, then the speed after 1 second will actually be negative 10 meters per second, but then they are asking you speed. If they're asking you velocity, then you can say negative. For speed, because it's a scalar, as we mentioned, then you cannot really call it negative. So for this, I'll just call it 10 meters per second. If you like to talk about the direction, it's fine. But again, speed is a scalar, so you don't actually have to talk about the direction. After 2 seconds, it's going to be 0 meters per second. And after 5 seconds, it's going to be 30 meters per second because you have plus 50. Originally, you have minus 20. So altogether will be 30 meters per second. Number 4 is about the graph. So let's see what graph it is. It's about a velocity time graph, so going down. So that means if this is saying downward, that means when you have negative, that is opposite of downward. So that means these are going up. Alright, whenever you see this, you may want to write down to remind yourself. Okay, and the question say which direction is the ball moving at point C? So obviously if this is going up, then these will be going down, and so C will be going down. At which point the ball is stationary. When you say stationary, that means the velocity must be 0, so that is point B. At which point the ball is at the maximum height. Okay, interesting. Because it is going up, right? When you say height, it's like how high up that you are. So when you hit 0, that's probably the turning point. And think about this. Whenever you are going up, right, then you are gaining the height until you stop moving. Just like I have a ball, let's say, I flow it up, like what happened in this graph. So I flow it up. Oops. The highest point is always when the ball start to return downward. All right, and that is the point where we just say stationary. So I'll flow it again. Okay, so you can try to flow, but be careful. And so that's why the maximum height must be the area from the beginning until point B. And so for the area here, we can calculate that must be 3 times the height, which is 30 divided by 2. So it's like 15 times 3, that means 45 meter. For the ball's acceleration at point C, in fact, for all the acceleration, you should know it is the same because, again, referring to what we learned in motion graph, in case you don't remember, go back to visit that part. This is a VT graph, and so if you want to find the acceleration, what you have to do is by checking its slope. And in fact, the question already told you that the slope is 10. I don't know why they wrote this. Alright, in case they didn't write it, you can check, you can calculate it yourself. Alright, it's just delta y over delta x. You can calculate. Actually, let me show you how I can do it. So you can do delta y, which is 30, like this point, 30, and then 6, right, for x, and then this is going to be negative 30, and then time is 0. So then you have 60 positive divide by 6, so that's going to be 10. The unit will be meter per second squared. So this is how you can calculate as well if they don't tell you in the question. So in fact, for all this acceleration, it's going to be 10 meter per second squared anyway, because they are on a straight line, right? The slope is always the same. Part G, which point does the ball have the same speed as when it was flown? So at the beginning, when it was flown, then it was negative 30 meter per second for velocity, or you can say speed is simply 30 meter per second, but it's going up. And so obviously, another speed that is also 30 meter per second, you can tell from the graph directly, and that is simply point C then. I mean, I don't think this is a really good question. I mean, it's very obvious. Okay, so that is all for this exercise. Okay, this is a pretty long video, so let me make a summary of what you learned in this video. So first of all, you should have learned that the different factors that affect the acceleration due to gravity, so that of course will affect the free falling time, including the height and also the planet and maybe the mass of the planet more precisely. And so for the acceleration due to gravity on the Earth's surface, remember it's Earth's surface only, it's going to be a constant, and the number is 9.81, alright, which we can round it up to 10 meter per second square in IGCSE physics. This is only assuming that there's no air resistance, then you will have such a gravitational acceleration. If there's a presence of air resistance, then of course the acceleration would be less, and that would of course make the free falling time longer. And in the air resistance, you learn about there are mainly two factors about how you can increase the air resistance, and that is increasing the surface area and also increasing the relative air speed. There are actually some other factors, at least there are two more factors that you can name. If you can think of those factors, please put down in the comment section below and I'll reply you to see whether you are correct. And that's all for this part of video and also this chapter note 2a. In chapter 2b, we'll focus more on the forces and how forces will affect the motion. I'll see you again in the next video. Bye.